the due date for experiment 2?
Experiment 2, I think I have it due next week right now, but there could be some flexibility. So I didn't grade your first one, your first memo yet, and I would like to grade it before you guys have your next one due. I just haven't had the time yet, so we'll talk about it. But right now it's set to be due for next week. But if I don't grade your first lab before next week, then I'll probably push it back. So I'll send out an email this weekend. So yeah, this lab isn't going to be due on the 13th. I don't know. Did I have that on the calendar or something? Or in the syllabus? It'll be due in a while from now. Okay, yeah, lab 2. So that's still, like I was just saying, right now that's due. I have that set to be due for next week, but if I don't grade all of your first memos by this weekend, then I'll push it back and I'll send out an email this weekend too. Just so I could be fair, so you guys can, look at my feedback for lab 1 and then make your corrections for lab 2. I'm going to write down a note to do that. Okay. All right, so today we're just going to be doing a lecture. So I don't know how far we'll get today because, like I was saying, we do have quite a lot of stuff to go over. So some of this will probably be talked about next class. So for this lecture, it's going to be about control systems. So let me share my screen. All right, so if you go to Canvas, you can go to weeks 7, 8, and 9. That's for this lab. All right. I really hate how Zoom has that box there. That's the chat. I'll just close out. Okay, so I have some files here for week 7, 8, and 9. Let's do that. Okay, so I have the lecture, I have the lab handout, and there's also another handout you can look at, which goes over the theory that we're going to talk about. So let's open up the lab handout. Just to kind of give you an overview of this lab. So this was like written a while ago, it looks like. So this is really experiment 3. Here it says experiment 4, but for us it's experiment 3. So the main thing we're going to do in this lab is we're going to basically model an airplane inside of Simulink. So we're going to give it some roll input. So we're going to assign some angle for how we want to have roll on our airplane, and then we'll model the output. So we're going to have 2 different systems that we're going to use, an open system and a closed loop system. So an open system, if we have some input, we're going to have some output, and we can't regulate that output. So if I say to have a roll of 5 degrees and we have a roll of 10 degrees or something, I can't adjust that. What I have for the input is what, it doesn't matter. I'm going to have some input and then I'm going to have some output. Even if it's not what I told it to do, I can't adjust for it. And then for the closed loop system, we can have some input and then we can monitor the output and then we can adjust for that if there's any errors. So we're going to be doing that for this lab. And we're going to be doing that by way of transfer function. So you maybe did that in vibrations, so fun stuff. Also in 308, doing Laplace transforms. So that's the name of the game for this lab. So you can read through this, but mostly this is what I just talked about and what we're going to talk about today for the lecture. And these are the kind of diagrams that we're going to make inside of Simulink. All right, so there is a lot of theory again. So we're going to go over some of it this class and then some next class. I kind of want to break it up so we don't have to spend 3 hours just going over the theory. So if you want to download the slides, you can download them on Canvas right here. I'm not sure if we're going to get through all of the slides today because there are kind of, a good amount here. So we may not get over or do all of them. Let me open them up here. All right. So I'm going to pull this up on my screen and you can pull it up on yours, but I'm going to write today's lecture on my iPad. So I'm going to share my screen with my iPad. There is an issue with sharing your screen with your iPad. I think they fixed it though. Okay, and I also haven't found a good way to make the resolution for this better. I was trying to improve it again last night, but I don't see any way where I can improve the upscaling. So if you have a big monitor, you're just gonna have to deal with the kind of crappy resolution, I guess. Okay, so before we get started, are there any questions either on the first memo or the second memo or just anything in general? Okay, I'm gonna assume that's a no. All right, so let's get started. Okay, so again, we're doing control system tuning for lab 3. You know what? I'm actually going to share my screen again. I should have already switched it. All right, so I have a few slides where I talk about what we're going to do. Okay, so the goals for this experiment, we're going to simulate a dynamic control system with block diagrams in Simulink. Going to gain experience with control systems, so we'll kind of understand what we're doing with these control systems for an airplane. We'll become familiar with the concept of dynamic stability and learn how to tune controllers. So this will be for our closed system using Ziegler-Nichols rules. So today we're mostly going to talk about the math part of it. So hopefully it's not too long, but we're going to do a lot of transfer functions today, kind of the theory behind them. Next class, we'll talk about more of the concepts for a closed loop system with the Ziegler-Nichols rules and kind of tuning our system. And we'll talk about the experiment a bit more as well next class. Okay, so I already talked about this a bit, but for this lab, we're going to model the dynamics of an airplane for different roll angle inputs and situations. So we're going to have two kind of models that we're going to have for this experiment. One's an open loop model and one is a closed loop model. So we're first going to have what I call smooth flying. So we're going to have some roll angle input that we have, and we're not going to have any disturbance torque on this for the situation. So we're going to have some roll input and that's it. So then we're going to model our response or the output of the system. So that'll be one part. The next part, we're going to smack an eagle. Yeah, they really specify an eagle, by the way. So we're going to have an eagle smack our plane, and then we're going to model that response. So we'll see how that impact affects our output for the plane. Okay, and then we're going to have a closed loop response. And in this case, we're going to have a feedback controller. So this will be able to monitor the output of our system and make adjustments, basically. And in this case, we're going to smack a hawk. It's a hawk this time against a plane and model the response. So this time, because we have a closed loop system, we should be able to adjust for that impact and then, have a nice stable system again. Okay, so now I'm going to close out of here Again, I would recommend to have the slides open as well on your screen. I think it's useful. Okay. Let me open up my slides. There we go. Okay, so we're going to be using a block diagram for the lab. So kind of like similar to what we've been doing before inside of Simulink, but this time our blocks, they're going to be transfer functions that we're going to develop ourselves. Okay, so kind of some review here for what a transfer function is. It's going to be a ratio of the Laplace transform for the output variable and the input variable. Okay. So I'm going to specify transfer function as just TF from now on. So transfer function TF. So we have a transfer function. It's going to give us the relationship for the output and the input of some part of our system. And from that relationship, we can basically develop an algebraic equation to model some part of the system. So you can kind of think about it, and we're going to do this later. We'll have some transfer functions, and we'll put them all together to make a system in Simulink. We're not going to use Simulink today, but this is what we can do. And we can model the acceleration, the velocity, and the position similar to what we did in the first lab. But in this case, we're going to model our kind of block diagram using transfer functions. Okay. Okay, let's go on here. So we're going to place our transfer function. We're going to place a transfer function in a block, and we're going to assign a variable to the block input and the block output. I'm just reading a slide and then I'll write it all out. Then we're going to obtain a differential equation for each transfer function block that we have. Then we'll assemble all of these blocks to make a system. And then we'll simulate the system from our developed equations that we just made. All right, so I'm going to draw out a little system here. Okay, so we're going to have some block here. Make it a bit bigger. All right, so here we have four blocks. And all of these blocks, they're going to represent some transfer function that we have. So for this system, we're going to have some input. So let's put that on the left. Okay, so that circle that I just drew right now, that's going to be a summation block, similar to what we had in the first lab. And attached to that summation block, we're going to have our input. So this is just arbitrary right now, but I'm going to call it I sub s. Okay, so that's going to go to our summation block. And then I'm going to fill in all of these blocks right now with transfer functions. So again, they're arbitrary for now. Okay, so what I have right here is basically transfer functions again. So once we go through a transfer function, you see that I have letters on each side. So when I look at the transfer function g1 of s, I have some input, which is e sub s, and then I have an output, z sub s. So basically these transfer functions, they're going to relate our output. So in the case of block 1, it's going to relate the output z sub s with the input e sub s. Okay, so I know it's kind of a little abstract right now, so we're going to go through a little example here. So let's say that block 3, g3 sub s, that's going to have a transfer function where we write out the output and the input, the ratio between the two. So, okay, so that's what we're looking at right there. So we're going to have the output and the input. So we're going to write this as x of s over u sub s. And that's going to be equal to s squared plus 3s plus 5. So this equation right here, 1 divided by s squared plus 3s plus 5, that's something that we're already going to have assigned. So we're going to assign that ourselves. We'll talk about how we can develop this equation later on. But this is the transfer function right here. So 1 divided by s squared plus 3s plus 5, that's kind of in this block here, g3 sub s. And this is kind of the equation that represents the relationship for the output x of s from the input u sub s. Also, a note, this diagram that we have here, it basically is going to represent the closed system that we're going to have for this experiment. So we're going to have 3 blocks that kind of make adjustments in our experiment. And then the block on the bottom, that's going to be a block that monitors the output of our system, and it's going to feed it back to the input so it knows, so it can compare the output to the input that we had for the system. Okay, so back to our example here, we have this transfer function that's given by 1 divided by s squared plus 3s plus 5. So we can kind of think of this like we have some input here, and we want to find x of s, which will be, it could be the position of our system. Okay, so what we're going to do is we're going to cross multiply because we want to solve for x. Okay, so if we do that, we're going to get x of s times s squared plus 3s plus 5. Okay, that's equal to u sub s times 1. And at this point, now we can take the inverse Laplace. So right now it's in the s domain for Laplace. And if we take the inverse Laplace, we can get it in the time domain. So if we do that, we're going to get x double dot plus 3x dot plus 5x equals u sub t. So now we have an ODE that's pretty familiar to us, and we can solve this ODE, and we can solve for things like the position of our object. Okay. Yeah. Okay. I'm going ahead to one slide here, and we can talk about basically what we just wrote right now. So I did the inverse Laplace. So maybe you remember doing that in vibrations, but I also have a slide that goes over it as well. Kind of some review. So I'm going to share my screen again. I wish there's a better method to kind of switch between the two screens. Okay, so on slide 8 of my slides, you can see basically some review for Laplace. So here we have basically the Laplace transform for y sub t, and we're converting it to the S domain. Okay, so you can kind of look down here, y sub t, that'll be equal to big Y sub s for the Laplace or the S domain. And then we have L sub y prime t, that's going to be equal to s big Y sub s, and then y double prime t, that'll be s squared big Y sub s. So you can reference this slide if you kind of forgot how to make those transformations. Okay, stop this, go back. Okay. All right, so for our experiment, we're gonna have an open loop response and a closed loop response. So if we have an open loop response, I already kind of talked about this, but it's on my slide, so I'll talk about it again. So if we have an open loop response, we can't adjust for the overshoot of our system, meaning that if we have some input, it's going to result in some output that can't be adjusted. So again, what I talked about, if I don't know, let's say we're like riding a bike or something, and I was controlling someone's bike, I don't know. But if I said I want to turn left by some amount, by some angle, then it would turn left, the bike would turn left, and it would have, whatever output. So let's say I want to turn left by 5 degrees, and in reality, I turned left by 45 degrees. So our output was different than what we specified with the input, but because it's an open loop response, I can't adjust for that. So I'm going to have that overshoot where it's a 45-degree turn, even though I wanted it to be a 5-degree turn. While if we had a closed loop response, I would have that 5-degree input, and then I would have that 45-degree output, but our system could read that and go, that's not right. We said we wanted a 5-degree turn, not a 45-degree turn. And then it could adjust for that. It could read that error, and then it can make adjustments to change our output to something that's closer to 5 degrees. Okay. Yeah, again, I guess I could draw it all out. I really wish I could have the slides though pulled up on my screen, kind of like I do once we make our models in Simulink, but it is what it is. So now I'm on slide 9 of the slide. So this will be some more Laplace review. Okay, so right now I'm going to draw out a little diagram here. Okay, so we're going to have two transfer functions, and it's going to basically relate our input and our output. Our input and our output, yeah. All right, so we're going to put an S in each of these blocks. And then here we have big Y sub S and Y sub T. So on the top, I'm going to write all this stuff out in the S domain. And then on the bottom, I'm going to write it in the time domain. Okay, so here I basically just wrote out a little diagram that's going to relate our position, our velocity, and our acceleration. We can kind of think of it like that. So our position is going to be y sub t, our velocity is going to be y prime of t, and then our acceleration is y double prime of t. So here we have a transfer function that's 1 divided by s to compute an integral. So let's write this out. So TF, again, that's going to stand for a transfer function. All right, so in the slides that I have, I kind of talk about it in my opinion, a kind of weird way. So a lot of this theory is from the other handout that I gave you. So on the slides, basically, we talk about this, that we're going kind of from right to left instead of left to right, which seems kind of weird. So I'll talk about both ways, but um, if we go from right to left, we're having a relationship from our input and our output. So here we have our acceleration on the very far right, and then we can compute an integral. So we're going to use a transfer function of 1 divided by s, and then that's going to give us a relationship for the velocity. Okay, so in that case, our input is the acceleration and our output is the velocity. Now, I think that's kind of a weird way to think about this because, our diagram shows it's going from left to right. So really, I think it's more intuitive to talk about it that way. So let's do that. So if we start from the very left, we have our position, y sub t, and then we're going to use a transfer function of s. And s, again, that's going to stand for the derivative. So we're going to have our position, take the derivative, and then we're going to get y prime of t, or the velocity. From that, we're going to take the derivative again, and then we'll get the acceleration. So just remember that s, for that transfer function, a transfer function of s, that stands for taking the derivative, a transfer function of 1 divided by s, that gives the integration. Okay, so now I just wrote out our input. If we're going from left to right, is our position y sub t. Then we're going to use a transfer function of s. Should have wrote that. So we're going to use a transfer function of s, which will take the derivative, and that'll give us our output, which will be the velocity, y prime of t. All right. And then again, we're going to go we're going to use another transfer function. So we'll have our input, which is the velocity, use a transfer function to get our acceleration. Okay, so now we're going to have a more immediate example that I think will hopefully kind of clear any confusion that you may have so far, because I think it's kind of been a little abstract still. So hopefully this example will clear some stuff up. Okay, so this will be somewhat similar to our first lab. We're going to have some mass here, and we're going to have a force, F of t, that's going to the right. And then we're going to have basically C times V, so some damping that's going to the left. In this case, we can think of it like the viscous drag that we had in the first lab, or you can think of it as friction on the ground if we have like a car. So if we imagine that this is a car and we're kind of moving to the right, I'll put that there. All right, so if we imagine that this is a car and we're going to the right, we're going to have some friction, and that's acting to the left. So we have our damping coefficient times x dot, just like we did in the first lab. Okay, so let's write out the equation of motion for this. I'm going to move this down. Okay, so the equation of motion, let's do that. So we're going to have mx double dot. And right now, of course, we're in the time domain. Equals negative c x dot of t plus f of t. Okay, so very simple equation of motion. So let's say that in this case, we want to solve for the velocity of this cart or this car that we have. Let's rewrite this a bit. Okay, so I'm going to basically write this in terms of v. So mx double dot, we can write that instead as mv dot of t. So on the left side, that's still the mass times acceleration. And then that's equal to minus c v t plus f of t. Okay, so at this point, we can now take the inverse, or we can take the Laplace transformation, and then we can start to develop a transfer function to relate the input and the output of our system. Okay, so we're going to relate basically our output, which will in this case be the velocity, and the input, which will be the force on this system. So let's actually write that out just so we can keep that in our mind. So the input, that's going to be our force. And then the output will be the velocity. Okay, so we're going to take the Laplace transformation of both sides. So let's do that. That's a beautiful L, by the way, for the Laplace transformation. Okay, so we have m v dot of t equals the Laplace transformation of negative c v of t plus f of t. Okay, and then if we do that, if we think about slide 9, which kind of had our review for the Laplace transformations, we can now write this out in the S domain. So let's do that. So we have m s big V equals negative c big V sub s plus f of s. So yeah, just remember those transformations for the Laplace. So we have what we had was m times v dot of t, and now we've converted that in the Laplace domain. So we have m times s big V of s. So just go back to slide 9 if you need some review there, but it should be pretty straightforward, I think. Okay, so we want to solve for the velocity, so we're going to get our v's on one side. So we're going to do m sub s, or m times s, v sub s plus c v sub s equals f of s. All right, and then we can do v sub s, that's times m times s plus c. Okay, so right there, I'm just taking v sub s outside, and then so yeah, I'm just doing that. You can imagine that if we distribute out right now, we would get what we just had. Equals v sub s. And now to make our transfer function, we need to relate the output to the input. So all we have to do here is divide, so v sub s divided by f of s equals 1 divided by ms plus c. Okay, so that relates our output to our input. So we have a ratio of the output divided by the input. So we have the output, which is the velocity, divided by the input, which is the force. And then that's equal to our transfer function, which in this case is 1 divided by ms plus c. Okay, are there any questions on that? Okay. All right, so I'm gonna draw this out visually now because this will kind of be how we implement this inside of Simulink. Because we're gonna have our input here. So on top we have it in the S domain, on the bottom in the time domain. Okay, so that's our force. And we're gonna have a block to represent the transfer function. There's 1 divided by ms plus c. And then the output is the velocity. Okay. Okay, so right now we have a relationship for the input, which is the force, to the output, which is the velocity. So that's fine, but what if we want to know the position of our car or cart, whatever it is? We want to know the position. Okay, so we can do that as well. So right now we have the velocity. So to get the position, we would have to integrate, and we can do that easily inside of Simulink. So all we have to do is use an integrator block, and then we can get our position. Okay, so if we take our kind of drawing that we just made, and we can add on an integrator block, and then we can get the position. All right, so I'm going to copy and paste our diagram here. And then to get the position, again, all we have to do is use an integrator block. Which is 1 divided by s, and 1 divided by s, that's also our transfer function to integrate. And then we get our output, which is going to be big X of s. And then on the bottom in the time domain is x of t. So that's pretty easy. So we had our transfer function already for the input, which was our force. And then we used our transfer function to get our velocity. And then all we have to do is use an integrator to get our position. All right, so we got another example here. Actually, maybe not quite yet. So we're about to do another example. Okay, so you can kind of think of this, I don't know, as just an add-on, I guess. So let's say that we have a transfer function, in this case, a g sub s, that's going to relate the input force to the output, which was the velocity. So let's write this out. Okay, so our transfer function is g sub s, and that's going to be equal to our output, which was the velocity, to the input, which was the force. And from our previous slide or our previous example, that was 1 divided by ms plus c. All right. So here we can also we related the input again, which was the velocity, to the position. So that was just our other block that we kind of added on. So let's call this transfer function h of s. And that equals x of s, which is the output for the position, over v sub s, which was the velocity. And that is equal to 1 divided by s. So that was our transfer function, just taking that integral. So if I wanted a transfer function to represent that entire system, so to represent this entire system here circled in purple, I can do that. So I can model this system with a transfer function in just one kind of block instead of using 2 blocks. So to do that, all we have to do is basically multiply our 2 transfer functions that we have in this system. Okay, so our equivalent transfer function, we're going to denote that by I sub s. And again, that's just going to be the multiplication of the 2 transfer functions that we already have in the system, which are g sub s and h of s. So if we multiply the 2 of those, then we're going to get 1 divided by s times m sub s plus c. Okay, so in that case, we can represent our system just with 1 equation instead of 2 equations. So that can kind of simplify some stuff for us or make it a bit more neat. All right, so now we are on the other example. So this will be somewhat similar to what we just did for this example with the car, but this time we're going to add on a spring for this system. All right, so I'm going to draw out the system that we have here. So again, it's going to be a mass. We're going to have a force. We're going to have a damping force and a spring. Okay, so here we have our mass. Here in red, we have the force. And then we're going to have some spring. I'll just draw it like this. Okay, so we're going to have some spring, and then we're going to have a damping or a damper as well. So we have K times X for the spring and C times X dot for the damper. So let's write out the equation of motion once again. So EOM, equation of motion, that's going to be mx double dot equals f of t, so that's our force, minus cx dot of t minus k sub x, k times x of t. All right, so pretty familiar so far. So we're going to develop a transfer function between the position and the input force. Okay, so first what we're going to do is take the Laplace transformation of both sides. Okay, so if we do that, we're going to get m times s squared times big X of s plus, so I'm moving some terms to the left-hand side here, plus c times s times big X of s plus k times big X of s equals big F of s. All right, so we took the Laplace transformation and we moved some terms around. So basically, I kept the force on the right-hand side and I moved the damper and the spring to the left-hand side. And of course, we took the Laplace transformation for all of our terms here. Okay, so what we want to do again is get a transfer function to relate to the output of this system, which will be the position, to the input of the system, which will be the force. So let's take out big X of s. So if we take that term out, then we'll have m times s squared plus c times s plus k. And that's equal to big F of s. Okay, so now all we have to do is divide through by f of s, and then we'll get our transfer function. So we have big X of s divided by big F of s equals 1 divided by ms squared plus cs plus k. All right, so all we did there is divide through by big F of s. And now we have our transfer function, so we have the output divided by the input, and that's equal to the transfer function. So the output is the position, the input is the force. Okay, so let's draw this out. I'm looking at my slides, and I just realized that I had an arrow pointing the wrong way, but it's okay. Okay, so let's draw this out. So we're going to have our block here, which is the transfer function. The output is going to be big X of s. The input is going to be the force. So in my slides, I had this arrow on the left. I had that pointing to the left, but really it should be pointing to the right. And then in the box, we have the transfer function ms squared plus cs plus k. Okay, so now we want to add on another transfer function here so we can model the velocity of the system. And then we're going to add on another transfer function to model the acceleration. Okay, so what we have right now is a transfer function that's giving us the position. So if we want to find the velocity, what do we have to do? Differentiate. So pretty simple. So to do that, all we're going to do is add on another block, which will differentiate our system. So we're going to take what we have right here, And we're going to add on another block, which will be just S, where S is going to represent differentiation. Nice. Okay, so that's going to give us, I guess I actually kind of wrote some more stuff out here. So that'll be S times big X of S, and that's equal to big V sub S. So we have our position X of S, and we multiply that by our transfer function, which is S, which differentiates, and that'll give us our velocity. Okay, so if we want to have an effective transfer function for this system, what do? We just multiply the transfer functions that we have. So we have these two transfer functions, and we're just going to multiply them. Okay, so our effective transfer function is going to be big V sub S over F of S, so our output divided by the input. And we're going to multiply our transfer functions, and this will give us S divided by ms squared plus cs plus k. All right, so now we're going to add on again, and this time we want to solve for the acceleration of the system. Okay, so we're going to do what we just did. We're just going to add on another transfer function, which will differentiate what we already have, and that's going to give us our acceleration. We're essentially just differentiating our velocity to get the acceleration. So let's take what we have. Let's copy it. This is why it's good to have some kind of tablet. I don't have to write everything out again. And then we'll take that, copy it, paste it. Okay, so we're adding on another transfer function once again to differentiate what we already have. So we're going to differentiate the velocity, and that's going to give us our acceleration. So on the top here, we have S times big V sub S, and that is going to give us big A sub S, or our acceleration. And on the bottom, I have V prime of t. That's, just the acceleration, which is A sub t. Okay, so now we want to find the effective transfer function for the system. So we're going to take what we already had, which we had up here. So that was s divided by ms squared plus cs plus k. And we're going to multiply it by our new transfer function, which is s. Surprise, surprise, what is it going to be? S squared divided by ms squared plus cs plus k. So we have big A sub s divided by big F of s equals s squared divided by ms squared plus cs plus k. All right, so that is our effective transfer function for our spring mass damper system with an external force. So this transfer function is going to relate the input for the system, which was a force, to the output of the system, which in this case is the acceleration. And our transfer function to model all of that is s squared divided by ms squared plus cs plus k. Okay, any questions? Okay, let's see. All right, I'm going to share my other screen again. We'll talk about the closed loop system for a bit. Again, I'll keep saying I wish I could show both of these at once. Okay, so we just finished that slide right there. So we're on slide 19 right now. Okay, so a closed loop feedback system. We already kind of talked about this, but this will be a system where we can measure the output, we can process the output, so we can kind of read and determine what the output is, and we can compare it to an ideal target value that we had that's going to change with time. So we're basically just comparing the output of our system to the input that we had. So we have this closed loop feedback system. We can measure the error that we have, and then we can make adjustments to decrease the error. So we're going to have our system. We're going to look at the output compared to the input. That'll give us the error. And then we can do something to adjust the overall system to decrease the error. Okay, so we compare that to an open system or an open loop system. We're going to give an input. We're going to view the output. And then we're going to cry when the output is bad and we can't change anything. So again, kind of relating back to our bicycle example. If I have an input of 5 degrees to turn left, and I have an output of 45 degrees, and I smack into a wall and break my arm, I can't do anything about that. I had some input, and then I get some output, and I can't regulate it with an open loop system. All right. So here is kind of what we would see for a closed loop feedback system inside of Simulink. My mic sound weird? It sounds like, I don't know, it sounds weird right now. I don't know. Okay, so this is kind of what we would see inside of Simulink once again. So we would have a summation block here. And then we'd have another block. I'll talk about this in a second. Here we have our transfer function. And then we would get our output over here. And then this block right here, big H of S, that would be a transfer function to look at the output that we have and then feed that back. And over here, where we can compare the output to the input, U sub S, and we can compute the error, which is big E sub S here. Okay, so we can compute the error, and then we can go, shit, this isn't good. We have some error here. We need to adjust it. And so this block here, case of P, that's going to be a block which is the proportional gain for the system, which will basically modify some aspects of the system to reduce our error. All right, so yeah, I talked about everything here. So H of S, that's going to measure, again, the output of the system. And inside of Simulink, we're going to use typically just a gain of just 1. Okay, but that'll be in 2 classes from now. Okay, so we have, again, this is the closed loop feedback system. And we could write out an equivalent open loop system. So yeah, let's do that. Okay. So I'm gonna go back to my iPad and then we'll go through this. I'm not gonna go through all of this math because it's just algebra, but yeah, let's do that. Share my screen. So annoying. Okay. All right, I guess I should draw all of this out. So I'm going to draw out the closed loop system that you guys just saw. Did I draw it up here? Yes, I did. Good. Kind of. Okay, I'm just going to modify this to what you just saw on the slides. All right, there we go. Okay, so from this closed loop system, we're going to make an equivalent open loop system. Okay, so what do we have to do? We need to have a relationship for the input and to the output of the system. So if we look at our output here, that's a big Y sub S. To kind of think about that output, we just need to look at the transfer functions that we have in our system. So the output big Y sub S, that's going to be equal to Kp times big G sub S times big E sub S. Okay, so Kp times big G sub S times big E sub S. Okay, so we're just multiplying by our transfer functions to have an equivalent transfer function. Okay, so that's going to give us our output for this system. Now we want to relate that to the input for the system, so we're going to kind of work through that. But before we do that, we can look at E sub S. So we're going to rewrite the transfer function E sub S. So E sub S, that's going to be the error that we have in the system. So what's the error going to be? So E sub S, that'll be, again, the error. That's just going to be the input minus our output. So our input is big U sub S minus the output, which is Y sub S. All right, and that's just the error right there. So let's rewrite Y sub S now. So we're going to plug in what we just solved for, which was E sub S. So we have big Y sub S equals Kp times G sub S. And now we're going to plug in for the error. That's big U sub S minus big Y sub S. Okay, so this part I'm going to skip some steps. Basically, it's just algebra. You can look at the slides if you want. But we're going to get big Y sub S over big U sub S equals Kp times G sub S over 1 plus Kp times G sub S. So that's the equivalent transfer function for our equivalent open loop system. All right, and to reiterate once again, that's our output y sub s divided by some input u sub s. So for us, once we do the experiment, our input is going to be some roll angle that we have. That's equal to kp times g sub s. Kp, that's our proportional gain. That'll help us modify our system to decrease the error. G sub s, we need to have an expression for that. We're going to do that in just a second. Divided by 1 plus kp times g sub s. Okay, so g sub s, we're going to say that that's a transfer function similar to what we had earlier. So that's going to relate some input force or input angle to an output position. Okay, I'll do 2.1. So we're going to plug in for g sub s. So say g sub s equals 1 divided by ms squared plus cs plus k. So let's go back in our slides here. So that's just this transfer function that we had up here, which was relating an output position to some input force. Okay, so if we plug that back into our equation that we have above here for our transfer function, again, I'm going to skip all of the algebra. If you want to look at it, it's in the slides. So let's plug that in. Okay, and then that's our new transfer function once we plugged in for g sub s. So we have our output y sub s divided by our input u sub s equals kp, the proportional gain, divided by ms squared plus cs plus k plus kp. All right, yeah, we could box this. Okay, we got a few more slides here. And so this would basically, if we wanted to draw this out for as a block, we already kind of have it really, but let's do that. So if we wanted to kind of model this inside of Simulink, this would look like our input here on the left. Okay, so that's it's kind of visually our transfer function or equivalent transfer function for our equivalent open system. Okay, so we have our transfer function, but what do we want to do with it? We want to find, or we want to solve for, in this case, the variable y. So our output, we want to solve for y sub t. So we're going to have to take the inverse Laplace for this transfer function that we have here. And once we do that, we're converting back to the time domain. And then we're going to have some ordinary differential equation that we can solve for to solve for y sub t. So let's do that right now. So I'm going to rewrite our transfer function. We're just going to cross multiply. Okay, so if we cross multiply, we're going to have big y sub s times ms squared plus cs plus k plus kp. That's equal to big U sub s times kp. So I just cross multiplied our boxed equation that we had. Okay, so I'm going to assume that our initial conditions are going to be 0. And we're also going to take the inverse Laplace. So take inverse Laplace. Okay, so we're going to get m y double dot t. Again, refer to slide, I think, 9 if you want to see a review on the Laplace transforms and inverse Laplace. Plus c y dot of t plus k sub p times y sub t equals kp times u sub t. Okay, so now we're going to assume that our initial conditions are 0. But before we do that, we want to have our output. So our output is going to be y sub t. We want that to match our input. So we'll say in this case that our input is going to be just equal to 1. So again, our input for the lab will be something like a roll angle that we're going to specify. But just to make our calculation simple here, we're going to say that u sub t is just equal to 1. Okay, so now I'm going to do, if we just rewrite that, take this, there we go. Okay, so we said that u sub t equals 1. So for our system, we want our output to match the input. So we want y sub t to equal u sub t, which equals 1. We want it to equal the input because we want a stable system. So let's think back to the bike. I want my input, 5-degree, like a 5-degree turn, to equal my output, a 5-degree turn. I don't want my input to result in some output like 45 degrees. So that's why we want our output here, y sub t, to be equal to u sub t, the input, which is equal to 1. Okay, so that's the goal. So right now we're going to assume from our differential equation here, let's call this equation 1. We're going to assume that the homogeneous solution is going to die out. So all we're going to be left with is the particular solution. Okay, so we're going to have to solve for that. So we have to use the method of undetermined coefficients. So let's do that. Solve for particular. Okay, and this is something that's, it's realistic. Our homogeneous solution is going to die out, and we're just going to be left with the particular solution. Assume homogeneous, or just homog. Solution dies out. Okay, so we're going to use the method of undetermined coefficients. So what we have here is y sub p sub t is equal to a. It's going to be equal to some constant, right? Because we have our equation up here, our ODE, that's equal to some constant k sub p. That's our proportional gain. Okay, so y sub p is going to be equal to a using the method of undetermined coefficients. We have to take the derivative. So y dot t, that's going to be 0. And then y double dot of t, that's going to be equal to 0. All right, so now we're going to plug in and we're going to have our initial conditions set equal to 0. So if we plug this into our ODE, what we would get is, well, let's first write this out. So plugging into equation 1, we're going to get m times 0, because we have m times y double dot of t. Y double dot of t equals 0, plus c times 0. Right, so we have c times y dot t, that's equal to 0, plus k plus kp. And this time we're going to have times a, since y sub t equals a, equals kp. All right, so we got to solve for a. A equals kp divided by k plus kp. All right, so this is going to then give us, if we plug in now to solve for our particular solution, we know that y sub p, that equals a, and we just solved for a. So we have y sub p of t equals kp divided by k plus kp. All right, so we have kp, again, that's the proportional gain that we're going to have in our system. K, that's stiffness constant. However, what did we say? We said that our particular solution, or output in this case, it should be equal to 1 because that was our input. We want our output to match the input. Okay, so that's going to be the same as saying that we need y sub p to be equal to 1. What do we have right now? We have y sub p equals kp divided by k plus kp. So the only way that I can have y sub p approximately equal to 1 is if we choose a really large value for kp. Once that value gets really, really large, we're going to have basically that really, really large value divided by that really, really large value. That's going to be equal to approximately 1. So let's write that out. All right, so we have the limit as kp approaches infinity. For kp divided by k plus kp, that's going to be approximately 1. Okay, so do we have any questions on this, on any of the theories so far that we covered? Again, we're going to cover some more next time, but from any of this, do we have any questions? Okay, So that's all the slides that I have for today. So we're going to cover a bit more, like I said, for next time. We'll talk about the effect of noise on our system. And then we'll talk about the closed loop system in more depth, where we talk about, go back to slide number 2. We'll talk about how we can tune our system using our controller that's, reading the error. And then we're going to tune it using the Ziegler-Nichols rules. All right. And then the class after that, then we're finally going to go into Simulink and model, the birds hitting our plane. Okay, so that's all I have for today. If you have any questions on either, I guess, Lab 2, you can stay and ask me. Again, I'm going to try to have Lab 1 graded by this week, sometime by the end of this weekend. And if I don't, I'm going to send out an email saying that Lab 2 is pushed back 1 week. So yeah, I'll send out an email. Okay. So that's all I have for today. So if you have any questions, again, just stick around. Yeah, so there's a question, can we use the FBDs for my slides if you reference them? Yeah, you can do that.